at other places in the world. I'm Professor D.K. Panda from the Ohio State University and lead this MVAPICH project. Thanks to many of you for joining us this 3 days event. So as you know, the objective of the MUG is an open forum for attendees, users, administrators, researchers, engineers, everybody, all the stakeholders, actually to share the knowledge, discuss all the issues of different MVAPICH libraries, including the OSU-INAM and OMB, which is the micro benchmark, and experience with large-scale systems, usage with a diverse set of applications, both HPC and scientific and AI applications. And also a lot of focus and discussion on optimizations, tuning. So the broad idea is to share the common knowledge and troubleshooting procedures. We started it 9 years back. So every year we have been continuing. Last year we had to do virtual because of the pandemic, and this year also. In the beginning, we thought that we can do a hybrid version, but it's not possible because of the several constraints. So we are going through virtual. So we have a very packed and excellent program for the 3 days. We have 36 speakers from 20 organizations as listed here. As of today morning, we have almost like 213 registered attendees, around 141 organizations, 21 countries from 5 continents. So here is just a sample list of people attending from all different countries. If due to any mistake, if your country is not listed, please let us know and we'll be very happy to update. So today is the first day. Typically we do the tutorials. The main conference will start from tomorrow. So today we have an excellent set of speakers from all different organizations. We'll start with Angel Pizarro from Amazon Web Services. He will be talking about planning of a HPC cluster on AWS using ParallelCluster. Then we'll have the tutorial from NVIDIA. Debinder Buredi and Manjunath Orental Venkata will be talking about UCC and SAR. After that, we'll have a tutorial from Rockport Networks. Matt Williams is the CTO of that company, will be addressing this tutorial to focus on addressing network congestion with a switchless ultra low latency HPC Ethernet solution from Rockport. And then we'll have a 1 to 1:30, a half-an-hour break. This is the Eastern time. You can translate to that your local time. Then in the afternoon, we'll start with a tutorial from Oracle. Marcin Jabloki will be presenting on running scalable clusters on Oracle Cloud Infrastructure. And after that, we'll be having 2 presentations from the MVAPICH project. Hari Subramani will be giving the tutorial on boosting performance of HPC applications with MVAPICH 2. And then followed by another tutorial by Arpan, Jain, Amir Safi, and Quentin Anthony on boosting performance of deep learning, machine learning, and DAS with MVAPICH 2. The program will end with a tutorial and live demo from ASCII Solutions. So they will be presenting on accelerating HPC applications with MVAPICH 2 DPU and then live demos. So the format, since we are going through a virtual environment, please use the QA boxes in the Zoom webinar to ask the questions, and the speakers as well as the volunteers and all will be answering this. The chats are disabled just because so many people are there. We just want to have a little bit of organized way of handling all the questions. But we also have a Slack channel. There are dedicated Slack channels. I think when you got your invitation, you would have received a link. Please log on to the Slack channels, and within that Slack, this is the link. And within that, you should be going to individual sessions. So every session has a separate Slack channel, so that will allow us to have a lot of asynchronous discussion over the 3 days. So I'd like to thank to all our sponsors. Without their help, we could not have brought this event to all of you. These are our sponsors: AWS, Oracle, Rockport, NVIDIA, ASCII Solutions, ParaTools, Ohio Supercomputer Center and Ohio State University. So with this, let me introduce our first speaker. Yes, so our first speaker will be, let me introduce.
You want me to introduce myself, DK?
I have a slide for you.
Oh, look at that. There you go.
Yeah. So just hold on for 1 minute. I'll share this. And, everybody can see it, all right? So we have the speaker, Angel Pizarro. He's the principal developer advocate at AWS. And he targets like HPC and scientific computing. His background is in bioinformatics, application development, and building system architectures for scalable computing in genomics and other high throughput life science domains. So let's welcome Angel, and then you can share your slides and get started. Okay?
Sure. Thanks for the introduction. Thanks for the invite. So where am I? I'm going to find it again. Sorry, folks. Here we go. And share. And go to full screen. And here we are. Okay. So thanks for the MVAPICH group for inviting me here. Really happy to sponsor this group. I think that networking, especially as it relates to scalable platforms, it's an old story, but it's a new story as well, as the different cloud providers, AWS inclusive, start looking at the massive scale that they are today and how that works with a lot of really different distributed workloads. So interesting domain, interesting problem, interesting community. Happy to be part of it. But one thing that's different, I think, about the cloud providers versus running your own HPC infrastructure, and I found this while running HPC infrastructure while I was at University of Pennsylvania a couple of decades back for genomics researchers, is that success for on-premise centers with basically a ceiling on their capacity, both with respect to data center space and just overall compute and storage. And success is not actually getting completely full, because then your queue wait times are too large, but actually guessing correctly over a multi-year horizon so that your capacity and the jobs that are scheduled in your community are as near to perfect as what your maximal capacity can hold, right? So that's sort of where schedulers came out from, and able to share resources across a lot of different users and workloads. Sometimes there's specialized resources that need scheduling, but back in 2008 or so, personally, I had an issue where I needed some additional memory to ask a question. This was a genomics process. It's actually proteomics processing, and it was an in-memory database, for lack of a better word, a huge sort of spectral match. We just didn't have nodes with enough memory, and it was reasonable to upgrade the cluster to handle this one question. It was, I believe it was under $50,000 to upgrade the whole cluster, and we would have had a larger maximal capacity and be able to answer that question on a regular basis. But it just so happened that at that time, AWS released a high memory instance. It had 1 terabyte of memory, or actually this was back in the days when 512 was big. So it had about 512 of memory. And so we decided to try an experiment and see if this question, which is just an unrestricted proteomic search, would work without having to spend $50,000. We ended up spending $4,000 to $5,000, if I remember correctly, in 2008 dollars on this question, which seems like a lot, but it turned out that it was not a good question. We didn't get good results out of there, and we actually saved ourselves $45,000 that we can put to other deals, right? So there are two things about cloud and scalable resources that slightly differ from on-premise is that the experimentation cost per unit price may be higher than what you would do if you amortized over a set of years and are in production for that question, but it allows you to quickly get your answer, whether that is worth it or not, at a reasonable price. And also it allows you to answer questions in a timely manner that you may have had to wait on the queue to get the amount of resources that you needed over a longer time frame. And we wholeheartedly believe that the most expensive, by far, the most expensive part of running HPC infrastructures or research groups are the people and their time. And if you enable somebody to be able to answer their questions that they have and experiment more, we believe that that in itself is a worthwhile endeavor, right? So this is a quote from Hyperion Research about, spend $1 on HPC, you get this much ROI. I'm not going to get into whether that's true or not, but the touchy-feely thing is that, being able to answer the question when you have it, and that access to resources is honestly, we think, is more important than going for the lowest cost possible. So we're within reasonable costs, and it's not perfect. We think we could do better, and we are furiously trying to do better in the services team here at AWS. But more importantly, we feel being able to answer the question and move science forward is the overall value for cloud and HPC cloud. It's a lot of different domains, as DK said. Mine is in life sciences, and specifically high throughput genomics. That's which is unfortunate for you guys because I don't deal with tightly coupled workloads. I deal mostly with loosely coupled workloads, which work fantastic for the cloud, and did not, about 5 years ago, 6 years ago, really weren't well suited for cloud until we started introducing some technologies. So these days, though, we are able to handle all sorts of different characteristic workloads, including tightly coupled workloads, which you all are mostly interested today. So I'll skip right over loosely coupled, accelerated computing, visualizations, AI, ML, high volume data analytics. These things are possible. Those are whole other sessions that we can talk about. But really, in this group, which is looking at networking at scale, especially for tightly coupled workloads, let's focus on that, right? So what does this type of HPC customer need that's looking at tightly coupled workloads? There's a very finite but really obvious set of customer requirements. And this is typical about how AWS looks at a problem. They first say, okay, instead of focusing on technologies, let's look at what folks actually need at a high level, and then work backwards from that customer need for solutions that may fit their needs. Right. So high performance, you need reliability, you need low latency, low overhead for getting your job done. You need, for at least for the network, a fairly consistent performance across the network with low jitter. And most of all, you need fairness. And for our definition of fairness, we're saying here that you're able to get the resources you need to answer your question in a reasonable amount of time, right, at a reasonable cost. So, which is not always the case, but and again, I'll call back to my university days where waiting on the queue because we were underfunded and oversubscribed was usually on the order of days for very big jobs, sometimes on weeks, right? And that was unfortunate, but that's the case in a lot of institutional clusters around the globe. Different story for the supercomputing centers. You guys are operating at a scale and a user need way greater than ours, but you do with what you have. So fairness and for the broad set of customers that are out there. So we worked backwards from there and thought about networking and came up with an answer that wasn't in line with the thinking historically about a new type of low latency network transport which we call the Scalable Reliable Datagram. It basically was a reliable, high performance, low latency network transport. It guaranteed delivery, but there were no ordering guarantees. And also it was a network aware multipath routing. So we were spraying out packets instead of having single path. And we were optimizing not for single packet speed, but basically overall, we were optimizing for packets eventually getting there at some reasonable service level agreement. So the tail latency and jitter, we really were optimizing for fast recovery of network events is the main part of what SRD was providing. And the way that we did this is we built a new type of network adapter called Elastic Fabric Adapter, or EFA. It provides up to 400 at the top end of certain instances, which I'll show you at the end of this presentation and tutorial. It provides up to 400 gigabits per second network bandwidth. It bypasses the OS and it gives you the GPU direct and RDMA access. All right, and that's all accessible on top of libfabric and higher levels up the stack. Right. Here's a small little GIF and diagram of how it's actually working. Basically, we worked with ANSYS Fluent over on the right to look at scaling across instances that did not have this this network adapter and SRD protocol. Green is ideal, and instances that did have that EFA installed and configured correctly. It's looking pretty good in terms of overall scaling, which is great. There's 83 nodes, so much faster performance. And the nice thing about this technology and this network protocol is that your storage is on the same backbone as the compute and communication layer. So there's no really islands of high bandwidth, low latency MPI communications. It's all running over the same network, which we feel and we've proven out through use cases. I'm not going to cover. I think Matt Coop will cover these on tomorrow's session, where he's looking at overall performance across networks and tightly coupled workloads. At the workflow level, we're very close to beating price and performance from other systems. Right. So how's this network stack go? Prior to EFA, you had to go through the whole TCP/IP stack and through network driver. That caused a lot of overhead. With the introduction of EFA and libfabric, you're able to go right to the kernel driver and the device for your message packet passing. Excuse me, I need some water. We've done work with Intel MPI. We've done work with OpenMPI. The MVAPICH group has done pretty excellent work with EFA. Hopefully, you'll see some of the results of that work in later presentations. So where is it available? Since the EFA was sort of a new network technology, it's not available on all our instances. So in terms of tightly coupled workloads, you do have access to it across a different set of architectures. There's a robust amount of Intel, especially our new M6i Xeon processors, and C5N, which is our workhorse for a lot of tightly coupled workloads and compute. NVIDIA, obviously, I'll show you across A100s, B100s, and T4 GPUs that have this enabled, so you can get GPU direct and RDMA access to your network paths. And you'll see some work from Matt about our Graviton 2 ARM-based processor that also has EFA enabled, and what that does with respect to, we compared it to running a Wharf and other algorithms on Intel and Graviton 2, and you can see what the price and performance characteristics are for ARM and for tightly coupled workloads, at least on AWS, which is pretty cool. So look forward to that tomorrow. All right, back to the main topic at hand. What are the components? What can you bring to bear? AWS has a lot of services, frankly, too many in my opinion, and most researchers could care less about 90% of them, right? What they really care about are these components here. One is the instances, like what are the underlying hardware that you can get access to, which I outlined before. Shared file storage services, I'll cover that at the end of this, but just know that we have block and object storage and parallel file systems out the wazoo options, and storage caches for instance, in-memory databases. These are all sort of possible as building blocks to fit together. And then you have management resources on top of that, and then 3D graphics virtualization, workstation visualization, so that you can have zero clients support, no local data, fast access between your data, your compute systems, as well as a bit of security, right? There's lots of ways of getting the data that you need, or maybe finding it from a third-party partner, the majority of which is Amazon S3, or object storage. It's shareable across region. Most folks put data in there when they're doing collaborations, treat it as the source of truth, and then pull down into shared file systems, parallel NFS file systems, when they need to crunch on that data fast, and then get the results back in S3 for sharing, right? So I think that's a pattern that I'll talk about a little bit later. But if you take nothing else from this talk, please treat shared file systems as ephemeral, give or take some unit of time, and Amazon S3 or some object system if you're on another cloud.
Angel,
Yeah.
I had a couple of questions. When you showed the performance, you showed a network graph, right? So how was the network communication path obtained? That seemed very interesting. What tool was used to get that communication path?
That's proprietary, and we don't talk about it.
Ah, okay.
Sorry.
Talk about the good stuff, do you?
Yeah, just know that we do spray the packet across the different paths on the network, and
Okay.
so that we can, if there is a packet failure, it might come in through another path.
Okay.
The SRD paper talks a bit about it. I'll put in the Slack channel about the protocol. I think there's a publication out there that we can share.
That would be very useful. Thank you.
Let me make a follow-up note about that. Sorry, hold on a second.
Sure. I mean, I can ping the question on Slack for you, so you don't have to.
Got it down. Okay, what else?
So you had one slide where you were showing the layering of the network stack. So there you showed that you had libfabrics, and libfabrics was going to the EFA driver. So we also know that you have a IB verbs implementation. So how does the IB verbs driver come here?
That's a question for Matt.
Ah, okay.
I'm not actually sure about that. Again, high throughput computing, fairly
Sure.
tightly coupled, but that's probably something you should ask Matt about.
Sure.
Most of,
yes.
the MPI implementations are on top of libfabric, pretty much.
Okay.
Mm-hmm.
Okay. So one other follow-up question regarding this. Let me know if this should be directed to Matt so that I can ask him. So you have two paths here: libfabric going over the kernel driver, and libfabric going straight to the EFA device. Mm-hmm. So what all communications or what all operations goes through one path versus the other?
Ooh, that's also a question for Matt that
okay.
he'll be able to talk way more intelligently about. I'm actually, Orange is user accessible, so I'm not sure which parts of the libfabric So I'm not sure the EFA kernel driver is actually accessible from the guest operating systems on
Sure.
instances, right? And that's where I don't want to misspeak. And Matt could tell you way more about it because
Sure
he
thing.
actually works
Sure
on the code.
Thanks, Angel.
Right. Right. All right. So getting back to this, just quickly, there's a bunch of stuff on here. Sometimes people could care less about orchestrating their stuff, honestly. So we put this a long time ago. We had created back when I was at UPenn, the way that I did my work was this great project out of MIT called MIT Ccluster. As open source and some academic programs go, it was a lifesaver for a lot of folks, but eventually people move on. It goes unfunded, and it essentially becomes abandoned, which it is today, unfortunately. But it was a great software. So we created a project called CFN Cluster, called CloudFormation Cluster, where it was a sort of a redesign of how would you do this today using that was a few years ago. How would you do it using AWS native technologies, these scalable clusters? That project got iterated on, and we released AWS ParallelCluster as an official AWS service, as opposed to an open source sort of orchestration framework. So this is supported by our support team. Our service, it's housed within our service team, and we do develop features against it, and add features as they come out for the underlying compute fleet where possible. So the team also integrates with other AWS services like FSx for Lustre, of course EFA, and the nice DCV team, as well as other sort of high throughput computing services that are out there. So it's an Intel select solution, which means Intel's vetted it for what's the best practice for standing up a cluster on AWS, which is great. So it does a lot for you, and the majority of this talk, or the latter half of this talk, after I get a little bit more about EFA, we'll show you how to use ParallelCluster. All right, so there are workshops galore. Obviously, I think all the cloud providers have a lot of documentation, but there are some workshops for running HPC workloads on AWS available at this address. If you go, there's actually workshops for a lot of different type of workloads on AWS, but there's a HPC category, and I'll point out two. One is how to use web services for HPC, which is collecting a lot of the different modules for working on AWS into this sort of Uber module. So you see here, not just the HPC cluster, which I'll show you a little demo about today, but also high performance file system, e.g. FSx for Lustre. It shows you simulations on AWS Batch, remote visualization with NICE, and more about EFA and distributed machine learning. So a lot of MIDI workshops all rolled into one for this one. You'll see it here. I'll link to it, as well as some others, including GrowMax and OpenFOAM. And more are coming. We've got a bunch in the pipeline. They should be released before the end of the year. Excuse me. The other one that I'll highlight is the SPAC tutorial. We used this for our ARM hackathon we held a few weeks ago. So it'll show you how to set up SPAC and reframe so that you can do performance testing of your applications, as well as installing items from SPAC, including MVAPICH, and be able to use ParallelCluster. So it's pretty cool setup. We had 33 teams using it for compiling and profiling applications on our ARM processor. The entire framework is here, including scripts for installing software, critical components to be able to do some work. So what's the demo we're going to show today? This is a sort of high level architecture. This is, I have a laptop here that has a Python installed and using ParallelCluster as an open source Python program. It's available on GitHub if you want to actually look underneath the hood. I'm the user. I'm not that bald. But essentially what Python does, much like CFN-Cluster, it actually creates CloudFormation templates, which are the machinery underlying automation of the operations of the cluster, like standing up the resources and linking them together in AWS. There are options also to allow you easy SSH access into the management node where the scheduler lives, as well as setting up remote visualization sessions. Of course, there's a simple storage, like I said, S3 for getting data. You can upload your data before you start any of this. And that data can be shared through our block storage called EBS onto the management node, which again gets NFS shared from the management node in this simple setup to compute nodes that start and stop based off of what we call AWS auto-scaling, right? So if there are no jobs in the queue, there's potentially 0 compute nodes out here. Again, this is configurable. Or if you always want 1 or 2 nodes available for jobs so that your jobs just go quickly, that's up to you. Go ahead and set the minimum to some number, and you always have some hot fleet ready and waiting to take jobs, and then scale according to what the size of the queue would be. All right, so because I am not brave, I recorded a session with ASCII, I don't know how you even pronounce that, but it's an awesome little program that will record your terminal. So let's play this. All right, and you can see all my spelling mistakes and my horrible typing. Right, like that. So here I'm using Ccluster version 2.11, and there's a couple things that I'm going to show here. One is I'm using the US East 2 region. Sorry about that, folks. All right, US East 2 region. I had a SSH key pre-made. There's a couple of them since this is a shared account for our group. Actually, this is my teammates' shared keys. These are not available to me, so make sure you pick the right one. You see that we have support for various schedulers. Most folks default to using Slurm, so that's the default. And there's some advanced features that I'll show later for Slurm. So we're using Slurm. You have your choice of operating system. I'm just going to use the default of Amazon Linux 2. And since I wanted to get started right away and show you information, I put a minimum size of 2 and a maximum size of 4. For the head node size, for the compute fleet size. And then the head node instance type, I use a C5, and the compute instance type, I'm using something within EFA, C5N. Network stacks, not important. These are pre-created. And it created at the end of this nice INI file, fairly easy to understand. Here's your AWS region that you define, how to SSH into your, if you've got particular needs of SSHing, you can have aliases there. What else do we have? Right. So you see here that the cluster template default. I'll show you a bit why that's important, which to use. When you run Ccluster, do you want to do an update or a sanity check when these nodes start up, which we both want true. And it went back here. Sorry. All right. So, and finally, where are we? Sorry. All right. Basically, I changed EFA to be enabled. It's disabled by default because honestly, sometimes you just need a high throughput cluster and networking isn't that important. For this audience, I assume you want EFA. And then here's your instance counts and what VPC settings are, right? So let's get back to it. so that was the INI file. There's a whole lot of options that you can do. Here's my second play. You're going to see, this is my actual typing speed. It's pitiful. I don't know how I do work. But this is the creation of the cluster here. Since it is CloudFormation, it takes a few minutes. I upped the speed by 40x, so that should give you some sense of how long this actually took. It took about 10 to 15 minutes for cluster creation. Scaling does not take that long, right? This is just, you're creating all of the resources, including the EBS volumes, the head node, the initial cluster nodes, and everything else. Right, and here I am SSHing into the head node, which again, I am a terrible typist. I forgot to put in the cluster name because you can have multiple clusters. So here I am in the head node, and you have all the tools you would expect, including how to inspect the queue sinfo, which I guess got cut off. But there you go. All right. So that's Ccluster in a nutshell. Even somebody as terrible as me, a typist as me, can stand up a cluster under half an hour, which is great. So what are other things that you can do with ParallelCluster? One of them is having multiple queues. One, you can have an EFA queue that has its own instances. You can also have a spot queue using our spot market, which is basically variable pricing, up to 80% savings, depending if you can get those instances. It's much better to split these two things up into separate queues, mainly because of you want the spot fleet to be diverse in nature. You typically don't want to restrict it too much. You want to have a mix of instances like a C5X large as well as T3 medium to take up different types of workloads, and you can use a specific instance type within that queue for your jobs if you have specific needs for the spot. So that's kind of cool. Multiple queues only works with Slurm right now. So be aware of that. There's a link at the bottom, which I'll also put at the end of this presentation, and I'll put into Slack on this particular tutorial. Another nice thing is being able to stand up a shared file system, parallel file system, if you're working on a bunch of data. This is pretty easy, right? Basically, you just say, I have a file system, MUG'21, and I want the storage capacity to be like 3.6 terabytes, right? And I want you to pull from all the files, or be able to do a file cache from this S3 bucket. So what it does is it places pointers to the file in S3, and on first read, it'll pull that file down as a cache the way that Lustre does. And then you've got access to it after that. So the first pull might take a bit because you're essentially streaming a file from S3, but after that it should be really quick access for subsequent reads. So microseconds latency on first read, or milliseconds on first read, and then subsequent reads microseconds. You also have an export path. This is not automatic. Basically, once you can tell FSX as after your job which files to bring back into S3, and again, to my point of treat object storage as your source of truth. Final thing I'll say is that we do have this concept of ultra clusters. These are large, fairly close located clusters of NVIDIA A100 equipped instances. These are their P4D instances that have EFA installed on the instances and available with the highest network throughput of any instance type on AWS available today at 400 gigabits per second. And then you have adjacent to it regular EC2 instances that can serve as your FSX file system. We're finding that a lot of customers are able to leverage this design and these clusters to get 60% lower cost train models, simply because of the capabilities of the A100, but also because they're able to use EFA for this non-blocking IO over something like a P3 instances, which have the voltas. All right, that's the end of my tutorial. There's a lot of source information. In particular, the documentation for ParallelCluster is really robust, including how it works, some example tutorials in there for MPI processes, the workshops, like I've mentioned before. The big collection one is the hpcworkshops.com here. You can get through the categories, but also the SPAC tutorial workshop here is probably the best workshop for the folks on this workshop, on this user group meeting to go to. And for MVAPICH, they have great guides on how to use it for AWS, as well as through SPAC. We're working with the MVAPICH group to merge these two things together for future versions of ParallelCluster, so that it's easier to get MVAPICH installed on a ParallelCluster through a post-install script. I'm going to end my talk there and look at Slack. If there's any questions, feel free to chime in there. All right.
Thanks, Angel. So I think we have a lot of time for question answers. So the attendees, please feel free to ask questions using the QA box on the webinar, or please go to the Slack.
Hi, Dr. Ben. I actually have a question to Angel about the ParallelCluster. I haven't put it on the Slack. I will put it later. So I love the auto scaling features of the ParallelCluster, and it's very useful to us. But I found so for example, if we create a cluster using ParallelCluster version 2.0, and then we upgrade the ParallelCluster to 3.0, and we found that it's not easy for us to make the cluster created by old version ParallelCluster compatible to new version of ParallelCluster. So is there any way that we can easily do that, or make
So are you talking about the configuration files between the two versions?
Not the configure. We actually made the configuration files same, but as the cluster is created by old version ParallelCluster, and once we upgraded the ParallelCluster to a new version, we are not able to do some operations like Ccluster update or Ccluster start or start or stop to the cluster created by old version. So
yeah. There might be a couple of things going on there. So between major versions are definitely not going to be compatible across the two, because the API is changing a bit. So ParallelCluster, if you look at the section in documentation on how it works, it uses a couple of other resources beyond CloudFormation to keep track of what's running, what's in your account, and including a DynamoDB table, and there might be some schema breaks between the two, right? So it's recommended to install ParallelCluster as a virtual environment so that you can control different major versions and minor versions of the cluster using virtual environments, so that you can keep compatibility between the two.
I see.
Yeah. Virtual environments are going to be your friend when you have version and API conflicts.
I see. Thanks.
So Angel, another question has been posted on the Slack. Is the MIG feature used for 800 GPUs? Is this feature used with MPI libraries on AWS to partition GPUs?
If I knew what the MIG feature was, I'd be, I'd be able to,
I'd be able to
answer that. Of course, yeah,
American.
maybe the NVIDIA folks can chime in because they should be fairly familiar with how it works. My guess is I'm gonna take a guess no, but I will follow up in the Slack channel on that question. How's that?
Sure. That will be perfectly fine. Are there additional questions? So, so Angel, you said towards the end, like this all-track cluster, I believe.
Right.
So that is you were saying that is the forward path kind of thing for AWS to proceed.
In terms of forward path, and what do you mean in terms of how we are looking at deploying?
Yes.
Infrastructure?
Yeah.
We're seeing a lot of demand for these P4D instances from the machine learning community. So we're definitely going to be expanding ultra cluster availability to regions and within a region expanding the available there as fast as we can procure them, quite frankly. So in terms of that being a future, yes. Is it the future about how we're going to deploy infrastructure? Nothing is ever certain in the cloud, and we have lots of different workloads. So I'm not going to sort of make commentary on what the future of AWS cloud is, but I personally can't see a future without looking at even more performant, tightly coupled like resources for meeting more and bigger tightly coupled workload needs. That's a sort of blanket statement.
Okay, thank you. There is another question posted on the Slack from Benson Muir. Do you have any I/O performance measurements for ultra cluster, and how does this compare to regular supercomputers?
So yes, there should be some blog posts and other things out there. I'll follow up with some links again after this talk about performance of P4D clusters for any given workload, and Matt might have some examples as well later. We tend to look at not look at single packet performance, right? So the benchmark suites are good and reasonable, but we tend to use that as comparisons between EFA and non-EFA on AWS as opposed to across different types of architectures. We let third parties handle comparisons across either other cloud providers or on-prem supercomputing centers, because that's just the way we operate. I will say that, in terms of looking at what is the thing that you should measure, we have a strong belief that you should measure with actual workloads and test cases that look at the entire workflow, not just micro benchmarks for when you make your comparisons. And the other thing that I'll mention is that oftentimes benchmarks for on-premise systems are run when they are freshly installed and not when they're under load by users. And it's important to remember that across all cloud providers, it's usually the case that the benchmarks are run while the whole network is under load for other workloads and other customers. And this is data that's coming from systems that will work the same when the system is under load, because it is already under load.
One general question. I know you mentioned about the MLDL. These are the new applications coming. How do you see the relatively, is that a very big demand compared to the traditional HPC, or I mean, I don't want a precise answer.
No. We can definitely talk about this. So there's a huge. So there was a Salishan session that we held about machine learning. And why is machine learning pushing our infrastructure so much more than traditional HPC workloads have, right? So there is a convergence of HPC and machine learning because they both share very similar characteristics of needing a large amount of coordinated compute with low latency networking so that the particular pieces can talk to each other, right? To address some of the bigger problems. But there's this funny thing that machine learning undoubtedly has pushed hardware much more than HPC workloads have, even outside of cloud, right? You look at NVIDIA's roadmap. You look at specialized hardware that's coming out specifically for training and inference. And I think that has to do with, money, quite frankly, right? The total market opportunity that's there for developing hardware that addresses that problem is much larger than it has been traditionally for either weather or CFD or molecular drug design. It's, you take all those tightly coupled workloads together, they might approach something in the order of what machine learning was 5 years ago, right? And it's just not. It's just a pure. The market is so much bigger, and the other thing is that tooling has really not, like, the difference of the advancement of the tooling for HPC and traditional HPC workloads just hasn't experimented very much over the years, right? There's lots of different frameworks, some of them good, some of them bad. For machine learning, you're always coming up with some new hotness, for lack of a better word, for how you should do machine learning. They try new languages, they out the wazoo of data structures and algorithms and everything else. You just don't see that in HPC as much, right? I think your group really does a lot of experimentation on what's possible with packet passing and network designs and everything else. It just doesn't have the same ecosystem with respect to the applications, the frameworks, and the underlying libraries. And there's just a lot of inertia in HPC within a particular domain to adopt something new, because usually the overhead of adopting something new or developing something new is so painful, and it tends not to work as well on the first iteration. So there's no, it's in this local minima of performance. And these are my own personal views. These are sort of things that we've seen, and we feel that if the HPC community can move forward in terms of its set of tools underneath the hood and adopt some modernizations, knowing full well this isn't as performant as it can possibly be, but it might enable new types of workloads or new ways of working that then get optimized later, I think the field will be much better for it.
Yeah, so in fact, we are heading towards that. In fact, if you would have taken a look, we are trying to enable the DL, ML, data science workloads through MVAPICH to stack. So we have an afternoon tutorial so that all the tools, whatever we have developed for MPI or HPC, can be directly useful there also. Yeah,
and we'd love to see it.
So we have just for the attendees, so we have an afternoon tutorial on that. I think it is at 2:30 or 3:30, I believe. So if people are interested, then they can attend it, kind of thing. So are there any? How about the debugging? How do you see the debugging issues for this new MLDL and all? Are you considering them together with tools, or do you think some separate work needs to be done?
Yeah, observability and traceability and debugging. These are things we're definitely looking at in terms from a service perspective. especially AWS batch and things coming out of a container land, because the services don't lend themselves to easy debugging. I think with ParallelCluster, since you're essentially running very similar tooling frameworks and security model as you do on-prem, the tooling can be lifted and shifted over there. It really has more to do with, like you said, once you're in an ecosystem that isn't, didn't have the strong profiling down to kernel flags as it could have. A lot of the lessons from HPC are actually probably going to be adopted by the machine learning community. It's just they've optimized for moving forward fast and applying models more than they have for optimizing specific frameworks and models, because they could deal with larger problems by adding more hardware, and our good friends at the hardware companies have been keeping pace with the questions that they've wanted to ask. I think we're getting to the end of that, and now we're starting to see better profiling and tooling and observability being applied back into machine learning, which is great.
So I had a follow-up question regarding tooling. So just like MPI libraries, for tools we need more let's say, system level access. Is there any plans inside AWS to enable folks outside of AWS to develop, like, let's say, network monitoring tools or other profiling tools which would need elevated levels of privileges?
I think we would love to hear what your needs are, honestly, about that.
So from my perspective,
because it's the same network that's the network is not just your own set of instances. This is a virtual network, so we have to be very careful about what we expose to customers, because we want to be very conservative about that, so that we don't essentially open up huge security holes. Right, so if we had a good handle on the types of monitoring and information that you want from network flows, I think that there's a path forward for us to create that for our customers. But it has, to be in aggregated along with, and I'll be very frank, much larger workloads on AWS, right, than HPC.
Sure, I completely agree. So we have a tool called INAM. So I was coming in from that perspective. So maybe if you can listen to the talk and I can follow up with you after that.
That'd be great.
Yeah. Thanks.
Okay. So thank you. So I think we are almost at the end of the session. So thanks again, Angel. So let's give a clap to Angel. So we'll switch to the next tutorial.